Swayam Prabha. Digital India. Educated India.
Hello everyone. Welcome to yet another session of our NPTEL on Nonlinear and Adaptive Control. I am Shrikant Sukumar from Systems and Control, IIT Bombay. So we are well into the 7th week of this NPTEL course, and we are already looking into algorithms for designing adaptive controllers for single and double integrators, matched and unmatched uncertainty systems. So the sort of algorithms that we are designing are not so far from the kind of algorithm design that will be required to drive autonomous systems such as the satellite in orbit that you see in the background. So what we were looking until last time was the design of the adaptive controller for the unmatched uncertainty case, right? So this we had essentially looked at how to use backstepping based methods in order to design an adaptive controller for systems that look like this, where the uncertainty is now in the state that is different from the state in which the control appears, right? So this is what is called an unmatched parameter system, right? So we of course saw the backstepping design, and it was a little bit more complicated than what you would expect for the matched case, right? And we also saw that one of the most important or key things to remember is that we had to design two different parameter update laws, which is the theta hat and also the mu hat, right? So we had to design the theta hat and the mu hat. That is, we had to over parameterize the system, right? So we had to over parameterize the system in order to be able to um, sort of complete the adaptive control proof. So in this case, although the uncertain parameter was only one scalar parameter, we had to design two different estimates for the same parameter. So of course, then we were able to prove tracking, or well, we did the stabilization problem, but as we mentioned, the tracking problem also would be a very straightforward extension of the stabilization problem. In fact, I would encourage all of you to try the tracking problem, right? So that's something I would write here. Try the tracking problem on your own. Okay. So now we move on to the next set of notes. I mean, again, please don't mind that it says week 8 and so on. We have been doing this, right? So this is merely to sort of organize the material. Yeah, so we are sort of, once we have completed one set of notes for that particular week, we have moved on to the next set of notes. And we will continue to do this because there is enough material to cover till the end, right? So we will move on to a slightly different topic or set of topics now. So we want to start off with the unknown control gain problem, right? So we will look at what is the unknown control gain problem. So this is what we want to do in hopefully the next couple of sessions, right? We want to look at what is the unknown control gain problem and how do you handle it. And as always, we look at the scalar versions of things here. And once we have done this unknown control gain problem, we will be in a very good position to actually introduce and look at the model reference adaptive control, which is probably one of the most popular adaptive control frameworks for linear systems. Yeah, so that's sort of the outline of what is in this subsequent lectures, right? So let's start looking at this, right? So I'm going to mark this lecture, right, as lecture 7.5. So this is the 5th lecture of the 7th week. So don't worry that it says week 8 in the beginning here. Yeah, that's merely for organization's sake. Yeah. All right, great. So what is the unknown control gain problem? So until now, we have been looking at unknowns uh, that are not in the control term, right? We've been looking at the unknowns in the drift term, right? So like in the previous week, we had, I mean, in the unmatched case also, we had the unknown which was connected to the drift term or the state terms, right? There was never any unknown connected to the control term, and that is what changes here. That is what changes here. Now we are again looking at the scalar single order system. Okay, just to make our treatment simple. Again, we will immediately after look at the model reference adaptive control case, which is the entire vector case. So we don't have to worry about missing any details as such, or this being not applicable to any real system you're working on. This is in fact with minor little extensions applicable to a lot of vector systems also. All right, great. So let's look at this system. All right, so what is this? This is x dot is a fxt plus b u. Now x0 is given to be x0 is the initial condition, of course, and both the state and the control are in real numbers, right? And the function f is of course taking the state and the non-negative time and giving you a scalar quantity r, right? And here the important thing to remember is that both a and b, right, a and b are unknown constants. Okay, in this case, there is an unknown connected to the state, which is what we have been seeing until now, but there is also an unknown which is connected with the control. All right, so this is new. And so then the question is, can we solve the same problem? So what is the same problem? The objective is, of course, that we want the tracking error to go to 0. That is, we want t goes to infinity, e of t goes to 0, where e is defined as the tracking error, which is the state minus the r. All right, so there may be some non-uniformity in us putting the time arguments with the states and the r and so on and so forth. Please don't worry too much about this notational inconsistency, if you may. We have just put in the time arguments wherever we think it's not very clear from the context. Okay, so when it's clear from the context, we don't put any arguments, but if it's not, we are just putting in some arguments of time. All right, so it's not nothing to worry about. If you want to be, of course, if you want to write articles and journal papers and conference papers in the field, then you have to be more careful and be very consistent with your notation. But here the purpose is instructional, and so we are keeping notation so that everybody can follow. Yeah, so the aim is more that you understand the material than be very precise and exact and consistent with the notation. So the purpose of the notation is so you can follow carefully. All right, great. Uh, so this is the tracking error. We always define this tracking error because this is the quantity we want going to 0. All right. So as usual, we assume that our the signal that we want to track is in fact smooth bounded with bounded derivatives. Right. So this is the standard assumption. So it is infinitely differentiable, it's bounded, and its derivatives are also bounded. So it's a very nice signal. Yeah. We don't want to deal with non-nice signals and so on. I mean, simply because of that, because in most physical circumstances, you wouldn't want your robot or any other mechanical or aeromechanical system, or maybe even an electrical system, to follow very bad trajectories. All right. So that's really what's the aim. We also make some assumptions on f, right? So what is the assumption? Is that f is bounded if x is bounded. Okay, so there are two assumptions. One is that the function f is assumed to be bounded if x is bounded. So it's a function of both state and time, but we don't worry about time. So I would in fact even say that for all t, and we also assume that b is non-zero. Yeah, that is the gain that is connected to the control is assumed to be non-zero. And this is a very reasonable assumption because if this is 0, then there is no term here. There's no control here. So there's no problem to solve. Honestly, we cannot do anything. Yeah. The system becomes uncontrollable, right? So this is very, this assumption is a very reasonable and a very fair assumption. So we don't have to worry about making a very infeasible assumption. And so is the assumption on F. Yeah. So so notice that we are only assuming that F is bounded when X is bounded. We are not saying that F is bounded for all states. If X goes to infinity, the function F is also allowed to go to infinity. Yeah, so it's not something like a sinusoid or something. It's not something as simple as a sinusoid, because if I had something like a sine X, right? Sine X, whatever, sine X times t or some such thing, right? This will be always bounded. This F will always be bounded, irrespective of uh, you know what is x and t, because it's inside a sinusoid. Yeah, but we don't care for, we are not restricting ourselves to functions like these. Yeah, we are even allowing uh, something like uh, say linear in x. Yeah, we even allow something linear in x. Yeah, so the only thing is we have to remember that it should not grow unbounded with time. Yeah, it should not go unbounded with time. Yeah, so that is one thing that we sort of have. So it could be something like x sine of t. Okay, something like this is also allowed. So this is a fairly, general enough set of functions. All right, it's a fairly general enough set of functions. So I wouldn't worry about whether we are restricting ourselves to a very, very simple class of functions or anything like that. All right. So whenever we talk about the problem setup, when we talk about assumptions, it's sometimes, or in most uh, times, it's critical to understand that these assumptions are not very, very restrictive on the system. All right, great. Um, Great. So now what do? We again do the standard steps, right? Whatever we are used to doing until now. We compute the error dynamics, right? So that's E dot is X dot minus R dot, right? And what is that? It's AFX plus BU minus R dot. Okay. So this is just obtained by plugging in the dynamics of X. Great. So now as usual, we do our design with the known case first. This has always been the, method of how we have been doing things. And so for the known AB case, we want to have a very nice target system. We've always been doing that too. We've been choosing a nice target system. And what is a nice target system? If I want to drive E to 0 asymptotically, it's E dot equals minus KE for some K positive. And this is the simplest possible linear, in fact, exponentially decaying system that I can think of, right? So we've also already worked with a system like this. And if you want to do this, what would I do? I would, so what we sort of do is we introduce this term, the minus K term, in the dynamics here. Yeah, earlier we simply chose the control, but now we don't directly choose the control. Just bear with me because of how we want to use the structure. Okay, so what we do is this minus Ke is the nice term, so I introduce it in the E dot, and then I also add a plus Ke, so that these two just cancel out and I have not really changed anything in the right hand side. Okay, so this minus K is there, and then I look at all these terms together. Yeah, because I want to sort of cancel this also, right? What do? I take the control gain B outside. Okay, so this is a trick. Okay, so this is a, I would qualify this as a neat trick. Okay, and lot of nonlinear control design is about such nice, neat, cute little tricks. Yeah, so don't, one should not be feel that this is just, a magical wand that I'm waving. These tricks are based on very good intuitions. All right, so it's a neat little trick, and a lot of nonlinear control, in fact a lot of mathematics, is based on doing such neat little tricks. In fact, a lot of proofs in mathematics that you will find are accomplished because somebody came up with a trick. Okay, so just because we use the word trick is not derogatory. Yeah, if you can actually come up with these tricks often, you will be a very, very good nonlinear control theorist. Okay, all right. So this is a nice trick. We just add and subtract this Ke, and then this Ke is clubbed with this guy. Yeah. How do we club it? We take the control gain B outside the bracket, right? And then I look at two different terms. There is one term where it is just a 1 by B because there is no unknown here in these two terms, right? So there's no unknown here. It's just a 1 by B. And there is another additional unknown here. So there is an A by B, F. All right. And then there is just a U because the B was pulled out of the bracket. All right. So this is a sort of rewriting of this term by pulling the B out of the bracket. This is also another trick that we pulled the B out of the bracket. Technically, you would have to do it, right? Even for the known case, because if I prescribe the control out of this, my control will have B in the denominator, right? And so we are essentially doing that. We're just writing it as such, okay? Because we want to rewrite or redefine the unknown parameters. That's the aim. Although as of now, we are saying that this is a known AB case, but we still want to redefine the unknown parameter or redefine the parameters of the system. Okay. And how do we do that? I now choose A over B as theta 1 star and 1 over B as theta 2 star. Okay. So instead of A and B being my unknowns, I have two new unknowns, which is theta 1 star and theta 2 star, defined as such. Now, remember that this is not over parameterization. I had two parameters to begin with, and I have two parameters now. So I'm not doing any kind of over parameterization. I'm simply doing a redefinition of the parameters. In fact, it is very easy to see in this particular case, may not always be the case. In this particular case, it is very easy to see that if I exactly estimate theta 1 star and theta 2 star, then A and B can be uniquely computed. A and B can be uniquely computed. So not a big deal. All right. So great. Great. So we understand all this. So some tricks and some redefinition of parameters. And what do we have? I choose my control in terms of these new parameters now because these are known, right? And that is minus theta 1 star F to cancel this out and minus theta 2 star Ke minus R dot to cancel this out. Remember, I don't need my control to introduce any new term because I already have a nice negative term here. So all I need to do is cancel these guys out. And once I do that with the control, I'm only left with this much. Yeah, so I achieve the target system for the known case. Yeah, this is exactly the same expression of control. The control expression is the same. If I had started here with the original system, this guy, right, and I had this target system, this is exactly the same control you would have obtained. I've just rewritten the control in terms of these redefined parameters, and this is going to be very helpful to me subsequently. Okay, this is subsequently going to be very, very helpful to me, and that is the whole reason why we are doing this redefinition. Okay, great. So this is the control, and with this control, I know that I'm left with only this. So of course, I choose a. All right, so I have not written that here, but I will choose a V, which is 1/2 E squared, and I will get a V dot, which is minus K squared, which is negative definite. All right, great. So this is what we've been doing, right? So this known case doesn't seem too significantly different except for some redefinition of parameters. All right, great. So now we move on to the unknown parameter case. So what do? We take the control law here in equation 1.5 and we replace the theta stars by the hats, because this is just what certainty equivalence principle has taught us, and this is what we've been using for so long successfully. So we don't want to change our successful formula or a success formula, right? So we replace the theta stars by the theta hats, okay, and these are of course the estimates, right? Now what happens? Of course, I don't get the desired E dot equals minus Ke, but I do get that plus B times the tilde terms. Okay, this is, I mean, this is very easy, right? I hope this doesn't confuse you, right? So because if you look at this, E dot is minus Ke plus B times theta 1 star F plus theta 2 star Ke minus R dot, sorry, plus a control, right? And now if you plug in this control here, okay, and you keep in mind this definition, yeah, it's very easy to see that the hats will give you theta 1 tilde here, this hat will give you theta 2 tilde here, and that's it. This term remains as it is, this remains as it is, and that's all we have. Okay, now the question is, how do I do the analysis now? Well, we try. Yeah, we try our usual idea. What do? We take the earlier Lyapunov candidate, which was half e squared, and we add to it quadratic terms in the unknowns. This is what we have been doing, with some, of course, adaptation gain in each case, right? So this is what we've been doing, right? So we want to continue doing something similar, right? Right. So then we start to compute the v dot very carefully. This contains e dot, and so E dot is simply this minus Ke plus B times theta 1 tilde F plus B theta 2 tilde times this. Right? This is based on the control law we have. Then we have derivatives of these terms, which comes out to be minus 1 over gamma 1 theta 1 tilde theta 1 hat dot and minus 1 over gamma 2 theta 2 tilde theta 2 hat dot. And we are, of course, yet to define the update loss. Right? We are yet to define the update loss. Great. Now, again, what do? We have this nice negative term coming from here, right? But then we have these theta 1 tilde and theta 2 tilde terms. So of course we try to club these two guys and these two guys. That's what we've been doing again, right? We've just been clubbing the theta tilde terms and using the theta hat dots to cancel out the errors, right? Whatever these terms, right? So in fact, I will write it out because it's not written here. So what will this be? This will be theta 1 tilde times B E F X T. I will take a gamma 1 in the denominator so that I get a gamma 1 here, and minus I get a minus theta 1 hat dot. Okay, and similarly I have a theta 2 tilde divided by gamma 2 times gamma 2 B and Ke minus R dot minus theta 2 hat dot. Okay, so these are the terms I get in theta 1 tilde and theta 2 tilde. Okay, now if I want to, and the other term is, of course, this is equal to minus Ke squared. So this is, of course, the nice term, nothing to do, but I want to get rid of these two terms. All right, and if I do want to do that, I just simply use theta 1 hat dot and theta 2 hat dot here. But well, look at what happens. Something rather bad, actually. Theta 1 hat dot is gamma 1 BE FXT and theta 2 hat dot is gamma 2 BE KE minus R dot. Everything looks nice except the B here. Yeah, this B is bad. Yeah, this B here is bad. This B here is a problem. It's a problem term. Why? B is in fact an unknown. Okay, and theta 1 hat and theta 2 hat are essentially being designed and defined so that we can identify this B, right? And so if we are still have an update law, right, and I notice that this theta 1 and theta 2 appear in the control, so it's not like these are for show. These are not for show. These have to be actually implemented. Even if you have a microcontroller and on a robot, then these have to be implemented in the microcontroller. These have to be integrated in the microcontroller. So obviously these are not for show, and they contain the unknowns themselves, right? So this is a circular problem, right? So that I'm trying to identify the unknowns using this theta 1, theta 2, which contain the B and the A, but then the B appears in their derivative, and that's not okay. Yeah, of course, so this is no adaptive control. So this is not an adaptive control that can be implemented. Okay, this is not implementable. All right, so that's why I put a big cross. So whenever I get any adaptive control solutions from unfortunately several naive students, and I find that, so the first thing I look for is if the unknown appears in the update law or not. Yeah, I don't have to look at the rest of the solution at all. Yeah, my checking becomes very easy. Yeah, that, because if you ended up with an unknown in your update law, then you made a wrong design. Your design is something that cannot be implemented. Yeah, so please don't make my life easy. Please make it hard, and design adaptive laws which do not contain the unknown in them. Okay, so this is wrong. Okay, the question is, what went wrong? Yeah, did we design the controller wrong? Did we design the Lyapunov candidate wrong? But it seemed like we had followed the steps that we were doing until now. So the problem is that the steps that we were doing until now do not work for this situation. Yeah, so we have to make a modification. The modification is not in the control law, which is still the certainty equivalence control law. So we don't make a change there, but we have to make a change in the Lyapunov function, right? So here we had chosen a Lyapunov function, which was very much motivated by how we have been doing things until now, with this just a quadratic term and adaptation game here. But now we have to do something different. We actually have to introduce an absolute value of b here. Okay, we have to introduce an absolute value of b here. Everything else remains the same, and just this new term shows up. All right, just this new term shows up. Okay, so what happens? Everything else is same again. Okay, the only difference here, right, the only difference that we see here is that because of this absolute value of b, which is again a constant. Remember, this is a constant. All parameters are assumed constant. There's no derivative with respect to it. But the second and third terms, which were simply these guys in equation 1.7, now have an absolute value of b here. So when I again combine this term and this term, my update law does contain something about b, but it is not the b itself, because we use the fact that b divided by absolute value of b is simply signum b. Yeah, I hope you understand this. Right? B is simply equal to absolute value of b times the signum of b. Okay, so although b doesn't appear now, which was wrong, signum b appears here. Okay, so everything else remains the same, just that instead of the b appearing, which was absolutely not available, I have signum of b appearing here. This, I would say, is a much more benign requirement. Okay, this is a much more benign requirement. Okay, what is the requirement? The requirement is that there is a signum of b that I need to know in order to implement this adaptation law. So the amazing thing is that in the entire adaptive control community, there is no other known choice of Lyapunov function or control which will help us to not know the value of signum b while implementing this control. Okay, so the only solution that is available in the community is what I have shown you. Yeah, and if you can come up with something that does not require the sign of b either, then you have done some magic and you will get a payment. All right, so this is actually something that's not possible yet. Okay, so if you can come up with something, excellent. So anyway, so with the knowledge of the sign of this control game, you can implement this adaptive controller, and you will get v dot is minus ke square, which is of course now not less than, but less than equal to 0. Right, this is not less than 0. This is only semi-definite because there were two other states, theta 1 tilde and theta 2 tilde. And therefore, you can complete the rest of the proof with Barbarat's lemma and signal chasing. In fact, you can show that limit as t goes to infinity, E of t is 0. Okay, the steps are standard. Yeah, you will just show that v is integrable. First, you obviously have stability, right? From here, I have, of course, uniform stability in the sense of Lyapunov, no problem. Beyond that, I will be able to show that E is bounded, that is L infinity. I know I can show that V is integrable because it is non-increasing and lower bounded, and therefore E is an L2 signal when I integrate both sides. So I obtain that E is both L infinity and L2, and then E dot is also L infinity, can be easily shown, and therefore by Babolat's lemma's corollary, you will be able to claim that E goes to 0. All right, excellent. So what have we seen today is how to handle unknown gains on the control in the adaptive control context. So until now, we had been looking at unknowns only connected to the states, that is in the drift terms. But now we have also seen how one can handle unknowns in the control vector field. Okay, and this is again something that is very, very naturally occurring. All right, if you have any sensor or any actuator which is misaligned, or you don't know the exact position or the orientation. For example, if I have a spacecraft with a control moment gyroscope as an actuator to help it rotate about its axis, right? And then I don't know exactly where, if it's placed in the center of mass or if it's oriented exactly along the body axis or not, then there will always be an unknown control gain. Okay, or you can also think of a quadrotor type situation where the thrust is actually some coefficient multiplied by square root of angular velocity of the propeller. Now this coefficient may again be an unknown quantity or not a well measured quantity, and therefore this also gets into the control gain and this unknown. Okay, so this is a very common problem, and we have given an adaptive control solution to control design in this context, so we can still achieve tracking. All right, great. So we will stop here, and I will see you again next time. Thank you.